Assalamu alaikum students. Today we are going to discuss IR spectroscopy. Infrared radiation usually refers to the part of the electromagnetic spectrum between the visible and microwave regions, and of the greatest practical use, the limited portion between 400 to 4000 per centimeters is usually very useful for the organic chemists. But there has been observed some kind of interest in the near IR and far IR regions also. Far IR region ranges from 200 to 700 per centimeters, and the near IR region ranges from 4000 to 14,000. And it is very clear that even a simple molecule like water and carbon dioxide, they can have a very complex spectrum. Organic chemists usually take advantage of this complexity when matching the spectrum with the unknown compound against that of the authentic sample. Usually we do it by peak correlation, which gives us an excellent evidence for the identity. Any two compounds, if they are not enantiomers, can do not have exactly similar IR spectrum. That is hard and fast rule. In IR spectrum, no two compounds can have an identical spectrum unless they are enantiomers. Although IR spectrum is characteristic of the entire molecule, it is true that certain group of atoms give rise to bands at or near the same frequency regardless of the structure of the rest of the molecule. So this creates a bit of confusion here in identification of the structures. It is the persistence of the characteristics bands that permits the chemist to obtain useful structural information by simple inspection and reference of generalized charts of characteristic group frequencies. Every compound has a characteristic band. We rely heavily on these characteristic group frequencies. Since we are not solely dependent on IR spectra for identification, we do have other analysis techniques. So our general plan is that we will present only sufficient theory to accomplish our today's purpose. That is the utilization of IR spectra in conjunction with other spectral data in order to determine the molecular structure. The importance of IR spectrometry as a tool of the practicing organic chemist is readily apparent from the number of books that are entirely devoted wholly to or in part to discussions of applications of IR spectroscopy. Infrared radiation of frequencies less than 100 are absorbed, and they are converted by organic molecule into energy of molecular rotation. But above that, the organic molecules generally convert energy into molecular vibrations between 100 to 10,000 per centimeters. This absorption in both cases below 100 or between 100 to 10,000 are usually quantized, but vibrational spectra appear as bands rather than as lines. Below 100 we observe spectral lines, but above 100 or between 100 to 10,000 range we observe bands. And because a single vibrational energy change is accompanied by a number of rotational energy changes, it is with these vibrational rotational bands, particularly those occurring between 4000 and 400 per centimeters, that we shall be concerned. The frequency or wavelength of absorption depends on the relative masses of the atoms, the force constant of the bonds, and the geometry of the atoms. There are three factors that are affecting the position of these bands or the frequency of these bands. Number one is the relative masses of the atoms, the next one is the force constant between the bonds, and then the geometry of the atoms. Band positions in IR spectroscopy are presented as wave numbers, whose unit is the reciprocal of centimeter. This unit is proportional to the energy of vibration, and modern instruments are linear in reciprocal centimeters. Wavelength was used in the older literature, and wave numbers are reciprocally related to the wavelength. So here we will deal with wave numbers. Wave numbers are sometimes called frequencies. However, this is incorrect, since wave numbers, that is mu naught, are equal to 1 into 10 raised to power